In 9.1 in Math 31, we start to talk about differential equations, and basically a differential equation is some equation that includes a derivative. So they give three different examples, something with a dy over dx, a dv over dt, which is the rate of change of velocity, and then a p prime is equal to 3p, which we probably won't get to this year. When we talk about differential equations, to find the solution to that differential equation, what we have to do is something called the antiderivative, and it's pretty aptly named. And the reason it's so well named is because it's literally the opposite of the derivative. So we're going to kind of do a little investigation here, and we'll talk about the antiderivative, and we'll come up with some formulas. And it really is going to be similar to what we did in chapter 3 when we learned about the derivative itself. So what they've done here is they've given us three different functions. So x squared plus 2, x squared plus 4, x squared plus 3. And what we should notice here is that when we take the derivative for all three of these functions, I get the exact same derivative. Now, I am not saying that all three of these f of x's are the exact same function. They're not, right? The first one is x squared move 2 units up. The second one is x squared move 4 units up. And then the third one is x squared move 3 units down. But what's really important is that by comparing three functions that are just different by translations, the shape of those functions are the same. So the slope of those functions are the same. And what becomes a bit of a problem is that in all three of these situations, we get the same derivative if f of x is equal to x squared plus a constant. And the reason that that's so important is that if I take the derivative of f of x like that, then I'm always going to get f prime of x is equal to 2x. So the question becomes, what constant? And that's going to be a really important consideration in chapter 9 and beyond, is that when we do the antiderivative piece, what we have to include is something called the constant of integration. Oops, I went the wrong direction there, sorry, which is a capital C. So what we use for notations is that if f of x is the function, then the antiderivative, we typically use a capital F to represent that, and it would include some kind of a constant there as well. Now, what we have to consider is that when we're doing the antiderivative, we're going in reverse. So the example, and we'll come up with formulas here in a minute. The example says find the most general antiderivative, so we're going to include the constant, and then the function is f of x equals, such and such. Now, what I'm going to do is I'm going to say that capital F of x is the antiderivative. Try to spell that right, the antiderivative I spelled derivative wrong. Antiderivative. Oh, I spelled it really wrong. Okay, I'm going to use an arrow now. I'm getting lazy. So capital F of x is the antiderivative of f of x. And there is a way to write that mathematically. It is the idea that if I took the derivative of my antiderivative function, I would get back to my original function. And we will talk about there is a different notation to write there as well. I'm going to write it at this point. If we took the general integral of f of x dx, we would get the antiderivative. Now, this means nothing right now, and that's fine. We'll get to that. Notation matters in math, so I wanted to just kind of introduce it now, but we'll talk about it in much, much more detail as we go forward. So we know what f of x is. It's x or 4x cubed minus 6x squared plus 11. And I would just like to show the way that we're going to do this is we're going to picture what function or what expression would I have to take the derivative of to get 4x cubed? And hopefully through the chapters that we've worked at, we recognize that that would be x to the power of 4. For negative 6x squared, the antiderivative of that is negative 2x cubed. And for positive 11, the antiderivative is 11x. Now, in order for us to kind of identify if we've done this correctly, it should be noted that if we want to check this, we could apply the derivative to go from our antiderivative to the original. The derivative of x to the power of 4 is 4x cubed, so that checks out. The derivative of negative 2x cubed is negative 6x squared, and the derivative of 11x is 11. What this allows me to say is that if f of x is given as that function, then the antiderivative is x to the power of 4 minus 2x cubed plus 11x. And then really importantly, there is a constant there. If that's 1, 2, 3, 4, 5 pi, Euler's number, it doesn't make a difference. That value of c could be anything, and it would still satisfy what this question gave us. Now, we'll learn later on that if they give us a little bit of extra information, we can then figure out what that capital C is. All right, they have a list of some of our particular antiderivatives. The one that I'd like to focus on a ton is our kind of anti-power law. And then these guys on the bottom, students typically struggle with. Now, if we want to talk about, what's going on here, to go from the left column to the right column is the antiderivative. And I'll spell it right this time, antiderivative. But just as importantly, to go from the right column to the left column, we would take the derivative with respect to x. And it's really important that if you keep doing it, you just go in a circle. That is the point of this. 9.1 is introducing the opposite operation of the derivative, which is named the antiderivative. All right, we're going to see these in use as we work through the examples. Wrong direction. My first example is just to find the antiderivative. I'm going to use the notation at least a little bit here. So if f of x is 2x squared, then capital F of x is going to be 2 over 2 plus 1 times x to the power of 2 plus 1 minus, and I'm going to put it as 1 over 1 plus 1 times x to the power of 1 plus 1 plus 7x, and really importantly, the constant. Now, what I'm doing there is I'm applying the rules on the previous page, but it is valuable that you can clean this up a little bit and say the antiderivative of f of x is 2/3 x cubed minus 1/2 x squared plus 7x plus c. Please make sure you understand that if you want to check your answer, I can take the derivative of capital F of x, and it'll get me right back to the function that they gave us, including the derivative of that constant, right? Because the derivative of constant is 0. All right, capital F of x for part B here. The antiderivative of cosine is sine, and the antiderivative of sine is negative cosine. And then we include our constant. Now, of course, we can clean that up, and we should write it as sine x plus cos x plus c. I would very much encourage you on a couple of these to check that that derivative takes us back to the original. All right, I'm going to write down the integration rule for this last one, and it is the idea that if we have e to the kx, then the antiderivative is 1 over k times e to the kx. And that's really important, that it allows us to work through term by term. And for this function, I'm going to say that the antiderivative is going to be equal to -3 divided by k is -1 for that first term. And then we're going to have e to the negative x still, plus 6 divided by the k value, which is 2, times e to the power, and it's still 2x. And then last but not least, you have to add that constant of integration. It feels like an afterthought in most of these questions, and at least initially it is. As we work through these more and more and more, you will get a little bit used to that constant of integration, but it really is a requirement. So try not to forget it. And I get that the antiderivative here is 3e to the negative x plus 3e to the 2x plus some constant. Make sure you can, let's do this one. I keep saying make sure you do it, and I'm not doing it, but I want to show you that if we want this to kind of check out, I have to make sure that the derivative with respect to x of my antiderivative takes me back to my original function. Now, I'm going to write this a little bit weird. I'm going to write it as capital F prime, because that does mean the derivative of capital F. And that's going to be 3e to the negative x times -1 plus 3e to the 2x times 2 plus 0, which means that the derivative of capital F of x is -3e to the negative x plus 6e to the 2x, which hopefully looks a little familiar because it's what we started with. And this chapter is very important. We're going to jump around a little bit. We do some chapter 9, some chapter 10, some chapter 11. This is the backbone for the back end of the course. We have to make sure we learn the opposite operations as well in math to make sure that we can solve, very complex situations. All right, just a few more, if I can go in the right direction. Very similar to when we did derivatives, it is a massive benefit to rewrite these, except for one of them with negative exponents. I'm going to write this as f of x is 2x to the -2 minus 5 times 1 over x plus x. And the reason that I want to do that is because if we look at 1 over x, the derivative with respect to x of ln x is equal to 1 over x. Now, this is on your formula sheet. The antiderivative is the other direction. I'll just put antiderivative here. I'll just put I'm going to put anti-d over dx. That's a bit of a cop-out there. And the reason that's so important is if you try to use your power rule, if I have x to the -1, if I try to use my antiderivative, I get 1 over 1 plus -1 times x to the power of -1 plus 1. This gives me 1 over 0 times x to the 0, which is, undefined. That is a problem because we can certainly have a function whose derivative is 1 over x. It's the natural log of x. So our power rule works really, really good unless we have x to the -1. So my antiderivative, capital F of x, is going to be 2 over 1 plus, all right, now I am just going to increase, oops, what did I do there? I put the k in the wrong place. So this is going to be the existing exponent -2 plus 1. That's going to be multiplied by x to the power of -2 plus 1. This will be subtracting 5 times ln x. And then we will be adding, I'll do the same thing here. It's 1 over the existing exponent plus 1 times x to the power of the existing exponent plus 1. Struggling to talk here. And then the constant of integration is at the end there. Now, you really should clean these up. As you get more and more used to these, it will get easier, I promise. What we're going to do then is I'm going to do this addition. So -2 plus 1 is -1. So this becomes -2 times x to the power of -1. I'm not going to touch 5 ln x. There's nothing I can really do there. Then I'm going to have 1/2 x squared. And then finally, I'm going to have the constant. And that's my antiderivative. That is a bit of a tricky one because of that ln x there. But make sure you have your formula sheet or these notes in front of you so you can check against the different forms as we move forward. All right, 2 more here. The last one's a little bit tricky for sure. But for E, what I'm going to do is, again, I'm going to rewrite one of those terms. I'm going to say that f of x is the sine of x plus x to the -3. And that means that the antiderivative of sine x is negative cos x. So negative cos x is going to go in place here, plus the original coefficient is 1. The original exponent is -3. I'm going to add 1 to that. It's going to be multiplied by the variable to the power of the original exponent plus 1. And then finally, I'm going to include my constant. So the antiderivative in this case is negative cos x minus 1 over 2 x to the power of -2 plus a constant. And again, if you're struggling with this, it's okay. Try to remember, when we learned this information back in, that previous chapter 3, when we learned derivatives, it was tricky originally, right? Out of the gate, derivatives are very difficult, but as we practice them, as we get used to the technique, it does get easier, right? And that's important to kind of keep in the back of your mind. All right, the last one here, we will eventually learn a couple different techniques for this, but what we're going to do for this particular question is we are going to use our double angle identity. Double angle identity. And we are going to say that our double angle identity is the idea that I'll write A's instead. So 2 sine A cos A is equal to the sine of 2A. Now, we don't quite have that left-hand side, right? We have sine x cos x, so A is x, but we don't have the coefficient of 2. But if I divide by 2 here, what I get is that the sine of an angle times the cos of the same angle is equal to 1/2 times the sine of double that angle. Now, what this allows me to say then is that the sine of x times the cos of x can be written as 1/2 times the sine of 2x. And the reason why that's such a big benefit is if I write that f of x is equal to 1/2 times the sine of 2x, this really takes on that, antiderivative form that we have. And then what I can do is I can substitute that in and go from there. So if we use our double angle identity, what I'm going to be able to say now is that capital F of x is equal to, I'm going to put the 1/2 here. I'm going to multiply that by 1 over the coefficient on the x, which is 2. And then the antiderivative of sine is negative cos. So we're going to have a negative cos here, and the 2x remains in place. We can then clean that up just a little bit. 1/2 times 1/2 is 1/4, but there's a negative in there. So this is equal to negative 1/4 times the cos of 2x. Take a minute and see if you can see where I messed up. There is a mistake in this final question. What did I forget to include? And it's the constant of integration. And where we introduce that is when we've taken the antiderivative. As soon as you've taken the antiderivative, you should be including that constant of integration. So yet again, down here, I'm going to include a constant there. All right, that's a bit of a tricky one. It definitely takes some practice to work with. Make sure you have your formula sheet as you're working through these questions, and I'll leave the assigned questions up on the board or up on the screen. Chip away at it, and if you're struggling with this, it is okay. Take it, slow, check the answer key, but of course, email me if you have a problem, and we can go through a couple more in a Zoom session or whatever that looks like for you.